All right, good evening everyone, and thank you all very much for attending tonight's event, which is called Hydrogen Headway. My name's Kalia Primer and I'm undertaking my PhD in the Adelaide Medical School here at the University of Adelaide, and I'm also your MC for tonight. Importantly, I'd like to start by acknowledging the Kaurna people, who are the original custodians of the Adelaide Plains and the lands on which the University of Adelaide's campuses at North Terrace, Waite and Roseworthy are built. So global warming is caused by increasing amounts of greenhouse gas in the atmosphere, and CO2 or carbon dioxide is a major component of that. That carbon dioxide is generated as a byproduct of fossil fuel use. It's something I'm sure we're all familiar with. But an alternative economy based on renewable green hydrogen can alleviate this problem. However, the current production of renewable hydrogen, which uses electrolysis, actually generates hydrogen at a cost that's unfortunately much higher than the current industry is willing to pay. So a method to produce cheap renewable hydrogen is going to be really essential in order to kickstart that economy, or the hydrogen economy. So tonight we're going to have the opportunity to hear how we can achieve this, how we can drastically reduce the cost of hydrogen to a price that's actually going to be commercially competitive. So during tonight's event, you're going to hear from Professor Greg Mether on the hopeful future of his research, where cheap, green, renewable hydrogen could displace the use of fossil fuels in sectors such as mining, heavy industry and transport, ultimately, ideally, leading to a reduction in atmospheric carbon dioxide concentrations. So Professor Gregory Mether is the immediate past head of chemistry here at the University of Adelaide, and previously he was an Australian Research Council Fellow and a postdoctoral fellow at both the University of British Columbia and the University of Sydney before coming to Adelaide. So you are going to have an opportunity to ask questions of Professor Mether tonight, so we'll be taking questions from both our in-person and our online audiences. So for our viewers online, thank you for watching, and I encourage you to submit some questions via the Q&A section at the bottom of your screen throughout the presentation. But without further ado, let's get underway. I would like to introduce you to our speaker, Professor Greg Mether. So would you all please join me in welcoming him to the stage.
Thanks, Kalia. Well, welcome everyone. It's nice to see the Braggs Lecture Theatre almost full again. It's been many, many years since I've seen it like this. And I'd like to let you public know that you act just like students, in that none of you like coming up to the front seats up here. So I feel like right at home. Okay, I've got a subscript to the title here. Hydrogen Headway, miracle fuel, or is it really just a ball of hot air? Let's investigate that tonight, and the introduction was quite good. I'm going to go over some of those points again. I'm not going to really go into great detail about what we need to do to decarbonise, so I'm going to accept that everybody here accepts that this is something that we need to do. But I think this slide is important because what we need to recognise is just what are the sources of these CO2s, because the solution to decarbonising is different for each of these sectors here. So you see on the left-hand side, the biggest contributor is electricity. So we know when we hear every day, we hear about new PV plants going in, new wind farms going in. We know that we're slowly turning our electricity grid from one that's fossil fuel based over towards one that's renewable energy based. And in South Australia, we proudly hold our heads up high, saying that we're leading the nation in that, where on average about 60% of our electricity comes from renewable energy sources. However, that's one of the easy ones to decarbonise. As you go down and you look at these other types of sectors, stationary electricity, transport, agriculture, another very, very difficult one, fugitive emissions, industrial processes. These are increasingly difficult to decarbonise. It's not a matter of pumping in green electrons to replace the energy usage in these sectors. We need something else. So the question is that something else? Could it be hydrogen? So different sectors require different solutions, and where does hydrogen fit into this overall map here? Okay. One of the things we also need to appreciate is that hydrogen comes from various sources. Hydrogen is coloured It's actually not, it's a colourless gas, but we now talk about the fact that it has colours. The type of hydrogen that we're talking about today is so-called green hydrogen, renewable hydrogen, that's typically, people think about, made from electrolysis, where the electrons or the electricity for that electrolysis comes from a renewable energy source. However, there are these other colours, pink, yellow, perhaps you haven't heard of white, that's naturally available hydrogen that you can mine. Turquoise, blue hydrogen, been a fair bit of talk about that in the media, about those sorts. And then finally there's the grey, the brown and the black. And these are the types that we're currently dependent upon for conversion of these fossil fuels into hydrogen. And you can see here I've got a downwards arrow, so as we go down there, generally approximately each of these methods, when you go from the green down to the black, produce more and more CO2 for a given amount of hydrogen that comes off here. Now, hydrogen, there's actually quite a lot of it produced in Australia right now. Just about all of it is produced from steam methane reforming of natural gas, so-called grey hydrogen. And you can see here, it's way down the bottom of my list here, it has a heavy CO2 footprint. So the question is, can we replace that grey hydrogen that we're currently using with green hydrogen? And this is where it makes sense. Certainly replacing or displacing this grey hydrogen with green hydrogen makes sense. But where else in our energy sectors does it make sense? Well, a little while ago, I became aware of this very clever so-called hydrogen ladder. So it was put out by Michael Liebrich and associates, and you can see here it sort of ranks where it makes sense to use hydrogen. You can see at the very top, it's all of those chemical type of processes. You see fertilizers, which is making ammonia or urea, hydrogenation, methanol, hydrocracking. Industries that are already doing some sort of chemistry that needs hydrogen, that is the best place for us to displace currently used grey hydrogen. Now, there's also been lots of talk about using hydrogen in a whole lot of other types of things, for example, cars. And you see that cars and other types of transport fall at the bottom of this ladder. It's actually uncompetitive. So here, and you can argue, where something should be approximately in this ladder, but here you can see clear distinction about where it makes sense to utilise hydrogen or green hydrogen and where it doesn't make sense here. So it's not going to be suitable for everywhere. So if anyone has that question, let's replace everything with hydrogen, it's actually not going to make sense. And it was said in the introduction, the reason comes down to cost. So what I'd like to do now is explore the underlying reasons why green hydrogen is so expensive. And for that, I'm going to put you into my first year chemistry class where I teach the thermodynamics section. So hydrogen 101 here. If we're going to make hydrogen from water, we need to put energy into the system. The hydrogen and the oxygen lie at a higher energy level than the water. So if we're going to drive that reaction backwards, we need to put energy in. We can think about this from an energy perspective or heat perspective, which we call enthalpy. And you can see here that the enthalpy range, the so-called delta H ranges, and given that there are 2 grams of hydrogen in 1 mole, so in my class I'd teach about it as energy per mole, but we often like thinking about it in terms of how much per kilogram, and this generates the so-called lower heating value and higher heating values that people talk about in industry when they want to know how much fuel do I need to make a certain amount, to make a process work or to get to a particular temperature. So these lower heating values. So useful to keep in mind, 120 to 142 megajoules per kilogram of hydrogen. And the difference between them is depending on whether you're generating hydrogen in the gas phase, that's what that subscript G is, or hydrogen in the liquid phase. So that's enthalpy. Now, if you want to then do work, do something constructive with that energy, you want to think about what's called free energy, or Gibbs free energy, given the symbol delta G. Here, the graph looks similar. The hydrogen and the oxygen lie at a higher energy level. The products, water in the liquid phase and liquid and a gas phase lie lower. And here, that difference is now slightly different numbers, but they're sort of the same order of magnitude. Now, again, in our first year chemistry, we would teach that there's a relationship between this so-called delta G and how much electricity it would take to make this hydrogen, to convert this water into that hydrogen and the oxygen. And this is where you may be familiar with this so-called 1.23 volts. That's how much voltage you need in an electrolyzer to generate your hydrogen and the oxygen. So you need to put energy in. Bottom line is, water is a relatively stable molecule. In order to make hydrogen, which is an unstable molecule, higher in energy, you need to pump in that energy, you need to do work, and that work is the equivalent of 1.23 volts. Now, typically, as you see here in my diagram, it's not just the energy between the reactants and the products. If you follow the pathway, the so-called barrier, you need to put more energy in, you need to surmount this so-called activation barrier. And for that, you need to actually put in a bit more energy, what we call the overpotential. And that's due to, we need to get over this barrier, it's due to the mobility, when we think about our electrolyzers of the charges, it's due to bubble formation, it's due to a whole range of things. So I want you to think, because I'm going to be referring to this later on, that this red arrow going from the bottom of H2O all the way to the top of that barrier, I want you to think about that as what we're going to be needing called the minimum band gap energy. So I'm going to just ask you to think about, remember a couple of things, but that's one of them I want you to think about, this so-called minimum band gap energy. Okay, so that's the energy requirements to make hydrogen from water. What's the cost? If that electrolyzer is going to be driven by electricity from the grid, we want to know how much that electricity in the grid costs. So what I've got here is a chart from CSIRO called Gen Cost. What they've done is through a variety of different methods of making electricity, what's it going to cost? And they're projected forwards 2030, 2040, 2050. And the plot that I'm showing here is the histogram for 2030. And you can see here, if you look closer on the left-hand side, it's in cost of, megawatt hours. And you can see here that towards the right-hand side, that we've got wind and solar photovoltaics as the lowest cost. And that's what you've been hearing in the news. Right now, and indeed next decade and onwards, the cheapest form of electricity is coming from these renewable energy sources. This is great news. But I want to focus on what that actual cost is. Remember, we need 142 megajoules per kilogram of hydrogen to make a kilogram. So that's the equivalent of 39.4 kilowatt hours. Now, electrolyzers are typically 80% efficient. You can argue some a bit higher, 90%. Let's take 80%, you get a nice round number, 50 kilowatt hours. That's how much energy it takes to make 1 kilogram of hydrogen. Now, based upon this chart, you can see the electricity, even for those cheapest versions, about $50 a megawatt hour, 5 cents a kilowatt hour, that would be $2.50. At $30 a megawatt hour, 3 cents, that's $1.50. That's the cost of just the electricity to make the hydrogen. Just the operating cost. Nothing about the infrastructure, the electrolyzer, it's just that. You can see if we are going to make hydrogen from electricity from this source, the cost of electricity is a significant component and it needs to come down a lot further. So the cost of electricity is a significant operating cost, even without consideration of the cost of the capital expenditure, CapEx. And in Australia, we have a target of $2. So if just about all that $2 is made up with the electricity, then doesn't leave us much wiggle room. Okay, you can go further with this analysis, bringing in the cost of the electrolyzer. So this is work done at ANU, Frank Giotso, where he's now coupled in the idea of the cost of electricity based upon these CSIRO Gen Cost assumptions, with some assumptions about the cost of the electrolyzers, and you end up with those two oblique dotted lines for two what people consider to be reasonable costs of the They've made some other assumptions about how much availability the wind power and the solar power is going to be available, and they've come to the conclusion that in 2030 we can make hydrogen through electrolysis for somewhere between just under $2 but upwards approaching $4. It's not really what we want to be hearing about what the cost of this electricity is going to be. So again, it's not just the cost of the electrons, it's also the cost of the electrolyzers. Now, what people haven't been talking about, and we learnt this when we had a speaker from Bloomberg NEF talking about electrolyzers that are being currently built in China. These aren't counted into people's thinking right now, but the numbers are coming out that these electrolyzers are a third or even lower in price. So it could be that these oblique lines have to be shifted down because of the cost of these electrolyzers, but nobody's doing it. It's uncertain as to why nobody's using these Chinese electrolyzers, and a lot of it has to do with reliability. But that's still, I mean, we're all still using many, many Chinese products, right? So anyway, that's out there, and happy to touch on that. Not that I know too much about that, later on in the question time. Okay, so what I want to come to is, can we produce hydrogen directly without going through the electrolysis route? And for that, I need you to understand a bit better what that source of energy is going to be, and that is obviously the sun. So what I've got up here is a diagram showing how much energy from the sun falls on the Earth across its range of wavelengths. Now the sun is this is where I've got a black body radiator. It means it's hot, over 5,000 centigrade, and anything white, you know, when you heat up a bit of metal, iron or something, you know, when you heat it up, it suddenly becomes red hot and then becomes white hot. Gives off light. That's what the sun is doing. Got fusion reactions going on, giving off light. That's the distribution after passing through the Earth's atmosphere. So those dips here are absorptions due to molecules, typically water and carbon dioxide in the atmosphere. But anyway, you see the general distribution, it sort of peaks at about 500 nanometers. So that's the solar radiation falling on the Earth, and that's what we need to utilize. If we're going to use direct solar radiation, we need to use that energy. So, emission of UV, visible infrared radiation, and each wavelength has a distinctive energy. And you'll see here on this bottom axis here, I've also converted the wavelength, which I'm sure we're all familiar with. 400 nanometers is blue light, 700 nanometers is red light, converting into what we call electron volts. Because when we're talking about materials, we need to talk about them in terms of this unit called electron volts. Okay, so what's a good solar radiance? Well, a good average is considered about 1,000 watts. If anyone's got PV on their roofs, you know that if you've done some calculations about how much power you can calculate, you typically use 1,000 watts or 1 kilowatt per square metre. Over an average day, you would accumulate that energy, and that's the equivalent of 25 megajoules per square metre per day. So we're going to use those numbers to calculate how much hydrogen we can make directly from solar energy here. So here's a map of Australia. Superimposed is what's called the solar insolation, so how much energy falls on the Earth. And you can see the darker brown bits, north of South Australia, across to Western Australia, are the most intense regions. So this is what we call is a good solar resource, those regions here. Typically, as you head to the coast, there's a bit of dampness coming in from the sea, so those tend to have slightly lower levels, but you can see comparatively, compared to the rest of the world, this is an excellent solar resource. There are very few places in the world that have as good a solar resource as we do. Okay, so let's assume that we can collect what I showed you on the previous slide, 100% of all that energy, we can convert it into hydrogen. How much would we make? 0.2 kilograms of hydrogen per square metre per day. 200 grams. If you consider a typical PV panel on your roof is about 20% efficient, that means you need 25 square metres of PV panel to make 1 kilogram. For those of you with about a 6 to 7 kilowatt system on your roofs, it means you plus your neighbour could maybe, on a good day, make 1 kilogram of hydrogen. Bottom line is solar energy is very diffuse, very dilute. It has a low energy density. So if we're going to come up with a technology that can capture that solar and convert it into hydrogen, it needs to be cheap. Really, really cheap. And that's what we're gunning for here. Develop a cheap technology that can take this very dilute energy source and convert it and concentrate that energy into effectively a fuel, hydrogen. Okay, so I'm going to be talking about 3 approaches to doing this. The first one is sort of something that you automatically think about, and that is if we take photovoltaic cells and couple them into an electrolyzer, but we do that really cleverly. We match everything. We match the operating current. We match the peak voltages. That's been done by a group at Stanford, where they've built, what have they got here? They've got really fancy photovoltaic cells. So this is what we call triple junction cells. These are the cells that go on the satellites that are orbiting the Earth. So 3 layers of photovoltaics. These are much more sensitive than the photovoltaics that we have typically on our roofs. Here, they've combined them with 2 electrolyzers. Don't want to go into the details, but electrolyzers basically broken down to alkaline and what we call PEM. And this is a PEM type electrolyzer. And what they did, they sort of increased the intensity of the sun, the solar intensity, to 42 suns to maximize, to match everything perfectly. And they achieved 30% of this so-called solar to hydrogen efficiency. So 30% of the light impinging on those photovoltaic cells were converted into chemical energy here. So this is an excellent outcome, as you'll see later on. The problem is these cells are very expensive, and the question is, how effectively can this be scaled up? This probably falls into the too expensive technology basket. So let's go further with this integration. Can we integrate these photovoltaic cells and these electrolyzers a bit more? And yes, you can. You develop what we call a photoelectrochemical cell here. So this now, we've made the electrodes in the electrolyzers actually the photon absorbers here. There are actually several different types here, and this is, again, there's a whole lot of differences going on here, but this, broadly speaking, just shows you that you can have these electrodes, and you can either put the solar energy resource onto one side or the other side, or both sides here. So typically what you need is these electrodes to now be able to absorb the photons. They need this band gap. Remember I used the word band gap before? The band gap needs to be above the energy to convert that water into hydrogen and oxygen. So it needs to be above that energy. We're now creating electrons, and the opposite of an electron is a hole, positive charge. We need to separate those. We need to drive the chemistry, so hydrogen evolution reaction, HER, and oxygen evolution reaction. We need to drive these so-called redox reactions. And then finally, when those molecules are formed, we need to get them off and bubbling away like that. So can we do that? This puts very stringent requirements on these materials. In addition to having all of the right energy levels, these materials have to be able to withstand water, be stable with respect to water. So that actually puts an additional criterion on the materials. But typically we can get solar to hydrogen efficiencies up to 20% in some of these devices, but they do tend to be quite complicated, quite small, and perhaps not very stable. So this falls in the, oh yeah, this could work basket. Now that said, there has recently been a Spanish company developed, funded by 2 very, very large industrial companies, Repsol and the gas company in Spain called Sunergize. I've been trying to work out how to pronounce that, and the more I say it, the more it makes sense. This is a type of photoelectrochemical device. They have now got a pilot scale working. They say it's been working for over 3,000-4,000 hours. It works an efficiency of 20%. It produces, you can see, relatively large quantities, so 100 litres of hydrogen per square metre per hour at a relatively high purity. So almost 6 nines there of purity. They are planning a demonstrator plant which is scaled up. They're constructing it now to be ready by 2025, where it's going to be half a hectare in size. The same sort of efficiency going on. So this is now one of these first technologies starting to break through from being a simple idea or a demonstrator in a laboratory scale and now going out onto on-sun demonstration. So we would say that the technology readiness level, which is sort of a ranking of how advanced the technology is, sits at about 6 out of a total of 9. So it's developed quite a way. It's past all of the proof of principle stages. So this is now, and this has got a serious amount of money with these large companies behind it. This is going to be an exciting place to watch. Okay, the third type of integration, and now we're integrating further and further and further. What we're now going to integrate is we've got all of our electrodes now compressed, condensed down into a single particle. The single particle is both electrodes, both the cathode and the anode, all encapsulated into one particle. It needs to do the same sort of thing. It needs to absorb the photons. You need to generate your charges, your electron and your hole. Those holes need to migrate to the relative surfaces where it drives your chemistry to produce your hydrogen and your oxygen. Very simple design. This is potentially the cheapest of them all. However, there are now even further stringent requirements on the energy levels need to be right, and the band gap needs to be right as well. So I'm going to show you some examples, and this is predominantly where my work is in this sort of field, what we call photocatalysis, where everything is brought back down to a single material, and the single material that has shown the best promise is a class of crystal generally known as perovskites. So perovskites are a class of crystal family. They're made up of 2 different metals with some oxides, and they have a particular structure. The first example was shown up here, calcium titanate, and it was actually first discovered in the Ural Mountains in Russia, and it was named after a mineralogist, Perovsky something. So that's why they're called perovskites here. So they have this general structure. The nice thing about these materials is it's open to a lot of chemistry. So a lot of clever chemists can come in and say, we're going to substitute one of those metals for another one, these so-called A and B sites. And what we can end up with is a material that has quite different and distinctive energy levels and band gaps. So it's hugely manipulable, which is exactly what we want here. They can also be made with high crystallinity, which you'll see in the next slide is a very, very important component as well. Now, this material has been developed and developed and developed, and there's been particular breakthroughs, especially in the last 10 years, where they've found by introducing a bit of either gallium or aluminium into the material, what we call the internal quantum efficiency has now soared. You can see it's sitting down here about 10% in about the 2000s, and particularly in the last decade, it soared up to, if you look at that vertical axis, over to 100%. What does this mean? This means that we effectively have a very efficient material that will absorb a photon, and those photons will almost certainly generate hydrogen and oxygen. So it's very efficient internally. There's one downside, and you're going to be hearing this a lot for the rest of the talk. The band gap is large. It's got a big energy, and that means it can't use a large part of the solar spectrum. It can only use a small part. We're referring to that point a few times. Nevertheless, a Japanese group has taken this material and they've laid them out in what they call photocatalyst sheets. These photocatalyst sheets are about 25 centimetres by 25 centimetres, and they've coupled them all together. There's a thin layer of water over the top, and all it is, it's like magic. You shine light on it, on this material with this thin bed of water on the top, and out comes hydrogen and oxygen, as you see bubbling out through the video here. So in 2018, they made these units that you've seen there about 3 square metres in size. Last year, they reported that they've scaled up. They're at the 100 square metre scale. This demonstrates that this technology is scalable and it's cheap. There's still one downside. They're using this strontium titanate material, but the problem is that with its large band gap, the amount of conversion you can get from your solar energy into your chemical energy is low. It's about 1%. So not what we want. It's about an order of magnitude away from what we want. But nevertheless, what this tells us is it gives us a blueprint for what we're trying to achieve. So we now know what are the key components of this material. We know it needs to be highly crystalline. We know that we need a regular crystal structure. We need different facets so that when the light absorbs, we generate our electrons and our holes. They go to these distinct facets. At those facets, we put catalysts. These are catalysts that assist with the chemical conversion process. That water needs to be broken down to produce oxygen and also to be broken down to produce hydrogen. These occur at these separate facets. And the final thing that we need is, because when you've got these catalysts there, as well as catalysing the reaction we want, they also catalyse the reverse reaction. So they convert our hydrogen and oxygen back to water, which is certainly something we don't want. So by suppressing this back reaction, by simply putting a thin layer of a metal oxide over the top, we shut down that backwards reaction. And we end up with a material that effectively converts 100% of the photons coming in into hydrogen and oxygen. Exactly what we want. It's now laid out for us. This is the path if we want to pursue this technology here. Well, this is work that my group has also been involved with. We have been involved with making these co-catalysts, putting them on. So we're making them out of what we call metal clusters. So these are size-specific metal particles. These are shown to be very efficient. We've also been making overlayers, putting these layers over the top to stop that back reaction. So there's some recent work that we've done here, and we've shown that it pretty effectively produces hydrogen and oxygen here. Now, what about lowering that band gap? Well, here's some other work that I've been doing with collaborators, principally based at North Carolina in the US, where we can show that, again, by clever substitution of atoms, different metal atoms, into that perovskite structure, we can lower the band gap. And you can see here we've demonstrated that we can take the band gap from 365 nanometers and push it well into the visible part of the spectrum, 556 nanometers. Again, some work that was recently published. So there's a lot of work going on these perovskites, which we are doing. Now, there's slightly different approaches. The approaches that I've been talking about are materials that are based on metals, perhaps not precious metals, but titanium, strontium, aluminium, etc. There are the equivalent metal-free type systems made up of predominantly carbon. So carbon nanodots with something called graphitic carbon nitride merged together. People have made a photocatalyst. You can see here it absorbs mostly in the UV, pushes a bit into the visible at the 450 nanometers, but it produces hydrogen and oxygen, and at a decent solar to hydrogen efficiency, now getting to 2%. Now, bizarrely, this work was published in 2015, and we have heard hide nor hair of this group since. So, a cloud of suspicion. Hope this recording doesn't go to China. Other materials. Very recently, polymer type materials. Polymers. Clever chemists can make all sorts of different polymers. Here we have a very simple polymer. There's a chemical structure there for those of you who know the secret language. And again, it absorbs the ultraviolet, perhaps pushing into the visible now beyond towards 500 nanometers. And for the first time ever, they demonstrated production of both hydrogen and oxygen with a simple polymer. This is the cheapest of the lot. These are dead easy to make. However, this suffers from a low internal quantum yield, quantum efficiency, and therefore also a low solar to hydrogen efficiency as well. This relates to some other work that I'm doing with a collaborator here at Adelaide, where we're now making blends of polymers coming together. These polymers now absorb in the entire part of the visible spectrum. You can see here it absorbs all the way through to 800 nanometers. It produces hydrogen. It's sort of done under cheating conditions, what we call sacrificial, but nevertheless we've shown that these materials might have the right properties for developing this. So there is a lot of work going on in trying to advance these materials to make these types of very, very simple direct solar to hydrogen technologies feasible. Now, how good can we make these materials? Well, here I like to think that I'm an optimist and think about what's happened in the analogous community in developing photovoltaics. And both these materials, perovskites and organic materials, make what we call the third and fourth generation of photovoltaics. And you can see here on the chart here that over the last decade, the efficiencies of these materials have improved rapidly. The bottom line is if you know what you're trying to achieve, if you know how to do it, if you know the architecture, the anatomy of what you're trying to achieve, then improvements will come with that effort. Sorry, that's not what I'm showing. That's what I meant to be showing there. So here, showing the plots of the perovskites and the organic photovoltaics as a function of time, increasing as we go along. So organics now 18%, perovskites now at 26% here. All right, how high does the solar to hydrogen efficiency need to be? There have been some technical and economic assessments done. They've been published on photoelectrochemical and also photocatalysis. You can see here they're quite dated. The most recent one on the right-hand side, published in 2017, but they all say effectively the same thing. You need to get your solar to hydrogen efficiency to at least 5% and preferably at 10%. And once you're there, you can make your hydrogen at $2 a kilogram. So that's the goal, that's the quest. That's what we're trying to achieve. Okay, I'm coming back to this solar spectrum. Because what does it mean to get the solar to hydrogen efficiency up towards 10%? How much of that solar spectrum do we need to absorb? So I've said before that minimum energy band gap is about 1.6 electron volts to get over that barrier. And so that's equivalent to about 775 nanometers. So that's just into the infrared part of that spectrum. So here I've got two plots. One plot both show the solar spectrum. One shows a material with a band gap of 400 nanometers. So if you think about this as the existing technology with strontium titanate. And then on the right-hand side, showing a material with a band gap that's equivalent of 1.6 electron volts. This is the theoretical maximum that we can achieve. The green bits is the amount of harnessable energy that we can get out of it. I'll come back to that in a second. But you can see here that the area of the green on the left-hand side is not very large, corresponds to about 4%. That's the best we can achieve with a material like aluminium strontium titanate. But on the right-hand side, if we can get a material, and I've already shown you some examples, and there are many others, that absorb out to the visible parts of the spectrum, we can start to approach our theoretical maximum that's close to 30%, which is well above what we need from those techno-economic assessments of 10%. Well above. So there's plenty of room to improve, and we don't even need to get all the way there. So there's lots of scope for improvement here. Okay, what about these red parts of these curves? You have to appreciate that when a photon comes in and it generates the electrons and the holes, it does a certain amount of work. And the amount of work that it needs to do is that energy difference between the reactants and the products. If the photon has higher energy than that band gap, that extra energy is not utilised. It gets what we call thermalized. That contributes to heating up. And what my group has recently done is shown is that if we take this excess energy, this thermalization, as heat and put it into the reactor, we can get improvements in the hydrogen and the oxygen efficiency. So this idea now that we can use these other parts of the solar spectrum to increase the amount of hydrogen and the oxygen that we can get out is a way of increasing the solar to hydrogen efficiency without increasing the band gap of the material. So this led to development of a patent which was submitted early last year, and excitingly for me, this garnered the interest of some industry partners. So a local technology firm called Spark Technologies, ASX listed company, and the behemoth Fortescue Future Industries, subsidiary of FMG, Fortescue Metals Group, led by a CEO who you're probably all familiar with, Twiggy Forrest. So we've created a joint venture, it's called Spark Hydrogen. We're pursuing this technology to make this conversion as efficiently as we can by using these additional thermalized electrons from the absorption process here. So I'm afraid I can't talk too much more about it because the patent is under wraps at the moment, so I'm limited by how much I can say here. So I don't want to infringe the patent. Okay, we're on sort of the home straight now. I just want to finish off with the work that's not just being done by me at Adelaide, but also more broadly, and why Adelaide is a great place to do this research here. I've got here a number of things showing you how hydrogen is brought together within the university. We have a research institute called ISA, Institute of Sustainability and Energy Resources, the umbrella arm for where all of the research happens. It's not just about the technology development, it's about the social license, etc., bringing cross pan-faculty contributions from everybody. Beneath that, we have specifically the Centre for Energy Technology, which focuses on utilising renewable energies to try to assist with the transition that I've just spoken about in our introduction here. So the CET has, over the past few years, created these two fora called High Temp, we've just finished the 2022 version, which is all about trying to bring in renewable energy into mineral and metal type processing, and also the HYPed forum, Hydrogen Production Technologies Forum, of which I chair as well. The university is also lead of a recently granted CRC called the HILT CRC, Heavy Industry to Low Carbon Transition, funded last year to the tune to run over 10 years to the tune of $70 million. The university is also leading a bid in a new CRC, Scaling Hydrogen, led by my colleague, also in chemistry, as research director. So this bid is about to go in here. We are all contributing towards this goal of advancing hydrogen as this replacement fuel to help us decarbonise the world here. Now, recently CSIRO made a report on all of the hydrogen-related activities in all of the research institutions in the country. And very, very pleasingly, of all of the universities, Adelaide was ranked first. You can see the highest number there, and mostly it comes from our cross-cutting work. What's that utilisation of the hydrogen? Okay, well, I just want to give you a couple of take-home messages and leave it at that. So, hydrogen does have a role to play. It's not the silver bullet, but it has a very, very important component that can't be taken up by anything else. It's going to be challenging for green hydrogen through electrolysis to be made at a level that's competitive, that industry will pick up and say, we would rather use the green hydrogen than the grey hydrogen. It's a challenge. It's possible, but it's going to be challenging. There are new emerging technologies for so-called direct solar to hydrogen efficiencies. I've shown you some snippets of the work that's being done in that field. And my view is, again, I'm saying I'm being optimistic, that by taking a leaf out of what's happened in the analogous photovoltaic field, I think we can improve the efficiencies to make this a technology that really will be transformative and help us with the transition to decarbonised world. Thank you very much, and I look forward to some questions.
Fantastic. Thank you very much, Greg. God, I feel like I've been plopped straight back into a first-year chemistry lecture, and I have to say I'm sort of regretting going the medical route. Maybe I should have stayed in chemistry. It was really, really exciting. So we have some time now for a Q&A, and I'm really excited to hear what everyone's got to ask. So for those of you who are in the audience, if you do have a question, please just raise your hand, and we have 2 roving mics as per the drill. Keep your hand up so our roving mics can see where you are. And for those of you online, please do submit your questions via the Q&A section. I can see we've got some in the audience already. Fantastic. We can see we've got one in the middle here, and then we'll go to that second one up the back in a minute.
Thanks. Hi, thanks for the talk. It was excellent. I'm just wondering, and maybe it's a stupid question, I don't know, but what happens to the oxygen? You know, you're splitting the water into hydrogen and oxygen. Is there a way you can use the oxygen to make the process more efficient? Or?
So certainly a lot of the way that fuel is used is in combustion. So when these things are combusted, I mean, Gus here, the director of CET, I don't think I need you to answer this, Gus, but I'm sure you correct if I'm wrong, but you can get a much more efficient combustion process going if you use pure oxygen rather than air, which contains about 20% oxygen. So you can still utilise that oxygen. There are also, if you make your hydrogen and your oxygen and you want to use a fuel cell, then you'd also need that oxygen to make that fuel cell. So there's a need to keep that oxygen. We always focus on the hydrogen, but the oxygen is a useful component as well. Oxygen is also a tradable commodity. So there's oxygen tanks, you know, obviously big in the medical industry. So it's been utilised. And then if the worst comes to the worst and there's excess oxygen that gets released to the atmosphere, at the scale we're talking about, it's not going to make a significant contribution to the atmosphere. It might rise a little bit, but I think that's not a concern that people have. So.
Fantastic. And we'll go to the question at the back there.
Hi, thank you for a really exciting talk. I was wondering how much more efficient does utilising the heat make the overall photocatalytic process? And has you and your research team completed a cost analysis of this compared to the previous examples you gave?
So I'm going to be cagey on the answer to the first question. I'm not going to say. But what we are doing is certainly we're doing a techno-economic assessment on the advantage, and it's almost complete, and there will be a ASX announcement for Spark Technologies coming in the next couple of weeks that will summarise the results of that TEA. So look out for that.
Okay, we've got a couple more questions. We'll come to this one down the front first, and then to the gentleman in the middle on the right.
I assume all of these materials have a lifetime. How recyclable are they?
Yeah, excellent question. We have to think about cradle to grave and life cycle analysis. So I'm not aware that anybody's tried to recycle them. Certainly the titania is in vast abundance. So you probably wouldn't add that, but certainly those co-catalysts that are added, they're precious metals. You would be wanting to recycle those, and I think that'd be relatively straightforward to do. So that's something that's certainly a component of the research that needs to be looked at. I agree. But what we need to do is work out what is the best co-catalyst, what's going forward. And I think that's the advantage of going to those organic ones, where, yes, they probably will degrade more quickly, but the need for recycling is perhaps not so high there as it is when we're dealing with those precious metals. So absolutely something that needs to be looked at.
You spoke of a target cost of $2 per kilogram of hydrogen as the sort of a maximum level you want to go to. The state government is committed, I believe, to building a hydrogen plant up north. I'm wondering what cost hydrogen they're going to produce it at.
Everyone is very cagey in the amount and the cost of the hydrogen that they're producing. So you might be familiar with the Tonsley project. You talk to AGIG, they will not tell you how much that hydrogen is being produced for. I'm sure it's not anywhere close to $2, probably not even a factor of 10 within that. So it's people won't tell you. They keep it very, very close to their chest because that seems to be a way that so one technology would distinguish itself against another one. So it's a wide open space, but it's already quite competitive. So I'm afraid I just don't know because those numbers just aren't being released.
Interesting questions. We have another one in the middle there.
You mentioned the fact that there are Chinese electrolyzers which are potentially a lot cheaper than current ones, maybe a third of the cost. Will this make $2 per kilogram hydrogen achievable or not, or will it potentially undercut your process?
So I haven't crunched the numbers, but you saw when I was talking about the cost of electricity that that's already a significant component. So you would need those electrolyzers to be effectively free to get the production cost to $2. So even though it's very, very cheap, you're still going to be struggling to hit the $2 mark.
Fantastic. More questions from the audience? Keep your hands up high. All right, we've got one down the very front here and then another up the back. We might go to this gentleman on the far right first.
Hi, Greg. Thanks for the talk.
Hi, Tristan.
I was just wondering, what are some of the operating costs of these photocatalytic cells? Because if I do throw back to my first year chem lectures, catalysts theoretically aren't used up in the reaction. So I was just wondering, what are some of the costs? Yeah,
that's correct. Theoretically, these things shouldn't degrade. What we know from, for example, that the large-scale system that I showed you being developed in Japan, what tends to happen is that the material is delaminated. So they're sheets, so they're put onto a glass substrate. So there's that comes off. So that seems to be the biggest problem. Other than that, those materials, if they were just suspended in water, seem to have a very, very long lifetime. In fact, now that I'm thinking about it, I remember that they've shown that those photocatalyst sheets will last for about 1,300 hours, which is equivalent to about 9 months operation in the field. And I think their performance degraded from 100% down to about 85% over that period. So it's a slow degradation process.
Thank you. We'll go to this gentleman here.
Oh, hey. Oh, can you hear me? Excellent. I'm not sure if this is outside of your scope of research, but I'm quite interested in understanding particularly if there's any applications that you're targeting for the generation of your hydrogen, and then also if there's any cost analysis for the logistics of bringing the hydrogen from the production plant to the end users, and if there's any interest in particularly, say, decentralized power generation on site.
From the hydrogen, you mean?
Yes.
Okay, so there are different views on this. My view is that it doesn't make sense to make hydrogen and then to use it again to make electricity. That just thermodynamically, it just doesn't make sense. You lose too much. In terms of what uses the hydrogen can be, I mean, I've outlaid that there's a number of industries that would like it. One of the conditions that they want is obviously a lot of these massive plants run 24/7. They want it all the time. So a process that only generates the hydrogen when the sun shines is not going to be completely acceptable to them. So that then introduces the concept of storage. So that's another whole side of it that I haven't even touched on today. So storage and also transport. When we're talking about transport, you need to know that there are effectively two ways that you can transport hydrogen. You either liquefy it completely, so it becomes a liquid, and that's that costs a lot of energy, which means it costs a lot of money. Or typically it's pressurized, but that still has a certain cost element to it as well. So people typically say that it would add about a third of the cost to do the liquefaction and the transport. So if you're at $2, then you add a third of that, so add 60 cents onto that cost to move it to somewhere else. So, yep, all part of developing the hydrogen economy, thinking about those sorts of steps.
So we have one more question down the front here, and then another at the back here.
Given that some people like me are very pessimistic about reaching the tipping point, will this technology be developed enough to stop us going past the tipping point?
Well, those tipping points, if my reading of is correct, we don't know when they are, but they could be very soon. So if I take your question as how long will it take for these technologies to be operational? Yeah. It's difficult to say. So we like to think that we'll have an on-sun demonstrator unit in a few years' time. I showed you the Repsol system. That's already a demonstrator plant. So it'd be interesting to watch that one as well and see if that gets replicated. So they're on the cusp, I'd say. So it's still going to be a few years before they scale up, but that's even true with electrolyzers. The electrolyzer companies that we talk to, I know that they are manufacturing them as quickly as that they can. They're scaling up those production as quickly as they can, and they just can't match the orders that are coming in for them. So it's just, the size of the problem is so massive, and that is a big problem. And scaling up there, it's difficult to understand just how long it's going to take to do that. So it's going to be a number of years before we get there. And are those tipping points going to be met? Yeah, I share your concerns.
Depends whether you're a pessimist or an optimist.
It's a very important question. Yeah. We'll go up to the one at the back.
Yeah, hi there. I just wondered regarding water quality.
Oh, there you are. Yep.
Yeah, sorry.
Water quality, yes.
I assume demin water's used, but is that consistent across all of these technologies, and has that cost been factored in?
Yeah, that's a good question. So, of course, with electrolyzers, you need pretty clean water to do that, and that's probably true with all of these technologies as well, because the water is in contact with all of these photocatalysts, so they don't want to be fouled up with chlorine or any organic gunk that's in there. So they need to be cleaned up. Just how resistant they are, it's not really known. All of these experiments will be done on fairly pure water. So, yep, there's going to be an aspect of cleaning up the water. But when you do look at the techno-economic assessment, not that I'm preempting what we're going to be revealing, but it does actually turn out to be a very, very minor component of the overall cost of the system. So.
Fantastic. We have time for maybe 2 more questions if there are more from the audience. Let's see, we've got one. Oh, this is one from online. Yep. I'll just wait for a microphone.
So we have an online question from Gunther. Are there photocatalyst demonstration plants? And if so, what can we learn from them?
So are there?
Yeah.
So I did show that there was one demonstration plant in Spain. That's all at the demonstration scale. And then there's the Japanese work. So apart from that, there's certainly nothing else out there that's of that scale that I'm aware of. So that's it. And those are going to be important places because that's where we're going to be doing a lot of learning about these technologies when they're scaled up. There's a lot of surprises. Doing it in the lab is one thing, but taking it out and showing it on sun and just scaling up, there are lots of unknown problems. So you need clever engineers to come and solve those problems. So that's why it's going to be a journey of several years before these technologies are proven. And that's all about advancing the technology readiness level. I mean, that's why you're at 6 when you're on sun, and then eventually you go to 7, 8, and 9, and then you talk about the commercial readiness level after that. So there's a process. It's fairly well known for advancing technologies. We just got to work at it persistently.
Do we have a final question? We've got one right at the back, and then I think that'll be a good point to wrap up.
Very interesting. I think with his catalysis processes, you talked about some of the uses of hydrogen. Is it actually possible to go on better actually and tweak these things to make one that spits out ammonia, turns the hydrogen into ammonia in the same process? Is there any things looking into that?
Absolutely. So.
Oh, even better, into fertilizer.
Yep. So there's my former lecturer at Monash University, Doug McFarlane, has created a very efficient way to produce ammonia from hydrogen electrocatalytically. So if you know anything about the way that ammonia is produced now, it's a process called the Haber-Bosch process, which was developed just after the First World War. So it's been around about 100 years. That one process alone to make ammonia consumes 1% of the world's energy and produces 2% of the world's CO2. So it's very, very energy intensive. So you're nodding your head there, so you know all that. So there's this other process that does that electrocatalytically. So once you've got ammonia, then if you need to make the urea or the other types of fertilizer, then that's a relatively simple chemical step to do. So it's all about making the ammonia. So yes, once you've got the hydrogen, you can make the ammonia. But there are people looking at the direct conversion. Can you extract the hydrogen from water molecules, mix it with nitrogen. So it has been demonstrated at very, very low efficiency, and I'm sure there are other people working on it as well. But I think this electrocatalytic route, I think that's going to replace Haber-Bosch.
Yeah.
That's my personal
And I
view.
imagine perhaps for some farmers, the possibility of on-site fertiliser production might be tantalising.
Yes, that's true as well. Yeah.
All right, I think that's a fantastic point to wrap up tonight's Research Tuesday's lecture. Would you all please join me in thanking Professor Greg Mecca? And thank you very much to you, our audience. What fantastic questions. Thank you everyone for coming along. Be sure to sign up for our mailing list to receive the latest information about Research Tuesday's related news. Thank you once again for tuning in tonight, and we hope to see you next time. Good night, everyone.